Hello, everybody. Good afternoon. Thank you very much for attending this presentation. My name is Nicolas Arroyo, and I'm very happy to be here. I'm a software architect at Bloomberg in the order and trade capture team. And for the most part of the last few years, my work has been related to performance and scalability. I do optimizations for existing systems, troubleshoot performance problems, and develop and promote profiling tools. Today, I would like to tell you about a fun story about a problem that really gave me a lot of trouble. It even has a reveal towards the end, and I think you'll find it interesting. Let's begin. Let's start by talking about what the thundering herd problem is. The thundering herd problem is a performance issue that happens when multiple threads wait on the same event and are all woken up at the same time. If only one thread can handle the event, the others waste resources with empty and unnecessary context switches. That's about it, right? You have an event that multiple threads are waiting for, typically an operation on a file descriptor. The event fires, all threads waiting become runnable, but only the first thread to wake up will handle the event. The rest take up a CPU core only to find out some other thread beat them to the event, and then go right back to sleep. Now, this could be a problem if the number of threads waiting for the event is large. Nowadays, it's not much of a problem. You don't really hear about thundering herds anymore. In the old days, what typically happened is that you would have multiple threads or tasks running except on the same socket. When a new connection arrived, every thread would wake up, even though only one of them would handle the connection. The rest would go back to sleep. This became a scalability problem when services started handling large volumes of activity. But kernel changes like the task-exclusive wake-ups solve this by allowing wait queues to have tasks flagged to exclusively handle an event. With this change, only one thread would be woken up, and that particular problem was solved. Then, when EPOL was introduced, multiple threads waiting on the same EPOL file descriptor would all be woken when an event in a target happened. Edge-triggered events solved this problem by waking up only one. Slightly different case, before kernel 2.6, when condition variables were notified with broadcast, all waiting threads would wake up, even though most of them would go right back to waiting on the accompanying mutex. Requeuing functionality was added to mutex that allowed to wake up only one thread and move the rest to the mutex queue while still asleep. And there were, and still are, other ways of triggering the thundering herd problem. But I think the main reason you don't hear about it anymore, at least at the system level, is that most of us don't write networking code anymore. This privilege is reserved to low-level library writers who are more knowledgeable about these quirks. So all of these thread-waking minefield is safely abstracted away from us. By the way, all of these examples are applicable to Linux, but there are similar scenarios in any OS you can think of. Now, I'm here to tell you about a situation that has an alternative way to cause simultaneous thread wake-ups in modern kernels, and by observing system API best practices. And it has the potential to affect thousands of threads in completely unrelated applications. Now let's go to the story. Like I mentioned before, part of my work is troubleshooting performance issues. So a friend pings me and tells me that he has a performance problem on a service call. We have service unicorn, and while servicing request eat, it fetches data from data store Rainbow. The service calls log their duration, so it's quite easy to browse and process them with the log aggregator. He tells me that the mean duration is close to 80 microseconds, and that sounds very reasonable, right? But my friend is very thorough, so besides looking at the mean, he looks at the slowest instances as well, and we should all do the same. And he finds some outrageous outliers that happen quite often, with latencies as bad as 20 milliseconds. This is a P95 histogram of the durations in a period of just a few hours. It has the 5% slowest and fastest instances trimmed out. And looks the way you would expect it to look, like log normal distribution, right? This is the histogram with all the data. And as you can see, the worst instances are as slow as 17.5 milliseconds. This is 250 times the mean value. This doesn't make sense. And even if it is a very small minority of fetches, it's not something that can go ununderstood. That's a real word. We need to figure out the impact of the problem. Back to the conversation. My first guess here, and probably yours too, is that these outliers happen during periods of extreme activity when the data store rainbow is saturated. So I asked about CPU usage, queue sizes, operations per second, etc. But it wasn't that. The problem happened all the time, even in periods of low activity, in every tier, in every environment. My second guess was, and maybe yours too, was that the records fetched from the Rainbow data store were too numerous or too large when these outliers happened. It wasn't that either. These outliers were happening with single fetches of average size records. My third guess was that maybe some background jobs in the data store were happening when these outliers were observed, something that blocked all queries. But no, there was only one background job running, and it only ran once a day. So I got started tackling the issue. I managed to reproduce the problem simply by launching an existing stress test in a nice development environment. And usually that is half the battle, right? Reliably reproducing the problem with the push of a button. So great. The first thing I tried is sampling profiling. Let's first sync up in sampling profiling, even though most of you know what it is. Sampling profiling involves taking a snapshot of a thread state, including its call stack, with a given frequency, for example, every 10 milliseconds. Typically, it is done in one of two ways: time-based, which is done with an OS timer, and event-based, which is more accurate but depends on hardware support and requires higher permissions. At the end of the profile, the call stacks are aggregated, and this gives you a statistical model of where in the code the task is spending most of its time. This gives you clues as to where to improve performance, right? I know what you may be thinking. This particular problem involves outlier execution times. And like I just said, sampling profiling usually implies aggregation, which destroys any information about the outlier instances. So all I will see is the average duration of this function, or the functions in bold, right? That's true, but sampling will show me the functions in call stacks in bold when I run this particular use case. So it will give me a good idea where to start looking. Also, if the problem is related to scaling, trying different types of loads may reveal code paths that grow or shrink in duration. Although we already know that the problem here has probably nothing to do with high traffic. Besides, I wrote a little sampling profiler I'm quite fond of, and when your favorite tool is a hammer, every problem looks like a nail, right? Now, let me tell you a little bit about this particular profiler and why I didn't just use perf. This profiler is both on and off CPU, meaning that it takes snapshots of the call stacks of both running and sleeping threads. This problem is probably I/O related, since it happens while querying a data store. And for I/O-bound problems like this one, an exclusive on-CPU profiler is not going to show long waits on events, which are possibly the problem here. Profiling I/O-bound problems is quite different from profiling CPU or memory-bound problems. I could do off-CPU profiling the classic way by probing the scheduler, but it is very disruptive and would hide on-CPU information, which is also valuable. Not to mention, root is not an option for me in this environment. This sampler is user mode or time-based, meaning that it uses OS timer instead of hardware events, so it requires the same permissions as the running task only. So I run the profiler in Unicorn service. If you're wondering why I didn't profile Rainbow instead, it's because it is a common data store and thus very solid. It didn't make sense to profile it, at least not at first, despite it being the query task. And I see this output. The profiler produces trace events format, which can be viewed with the Chrome browser. And it is very similar to flame graphs, as you can see, except it is upside down, the functions on top call the functions on the bottom. Just like flame graphs, the thicker the call stack flame, the more samples were captured on it. So for example, here I can see that the program spends more time on function fetch from Rainbow than on function nothing interesting. Unlike flame graphs, however, it separates the information by thread, as you can see. Every lane is a thread. And it also colors on CPU and off CPU call stacks differently. As you can see, off CPU is colored blue and on CPU is colored gold. This allows me to tell apart CPU heavy from IO heavy code paths. If we zoom into it, we'll see here where the request is reserved, the request is served. And as we would expect, this is where most of the time is being spent. Down the stack, we see fetch from Rainbow, which is the function we're trying to optimize. We'll add it to our suspect list. If you go down the stack further, you'll see many functions being called by fetch from Rainbow, and that we can add to the list of suspects. Functions play with light and color main are the ones that take the longest amount of time. So I looked at their source code trying to find some obvious issues, but nothing stood out. In fact, I looked at source code of all the functions in the suspect list, and I saw nothing noteworthy. But like I said before, the aggregating nature of sampling doesn't tell me anything about unusual execution times or outliers in these functions. So it is time to switch gears and try something else. As you all know, there are two main types of performance profiling. While there are a few other types, arguably the two most common methods are sampling and code instrumentation. Like I said before, sampling takes snapshots of the threads call stacks, it aggregates them, and it gives you a statistical model of where time is being spent on. On the other hand, instrumentation is about inserting code at the entry and exit of every function or code block of interest, taking timestamps at both places, and then emitting this information as spans. The timestamps can then be processed to calculate latency of function invocations. By the way, I'm talking about code instrumentation in the context of performance profiling only. There are many other types of instrumentations for different purposes. This can be done in a number of ways: by manually inserting calling code, logging code, by using telemetry libraries, statically modifying the binary ahead of execution, or dynamically modifying the running task, which is what we will do. As you can imagine, using it on every function in a program, regardless of the method, can be very disruptive to the point of being unusable, especially with large binaries with millions of functions. It is also not very useful in functions with very short durations because the bias it adds may be longer than the actual duration of the functions. But if you selectively choose a list of suspicious functions, like the one we have, it can reveal information that sampling profiling hides. Let's see an example of how the information provided by both profiling methods is different. On the top, we have a sampling trace, and on the bottom, we have an instrumentation trace of the same program. I also use trace events format for visualization of instrumentation traces, but this time displaying different information. This time, it only shows me blocks for instances of function executions, no call stacks, just the time where each function execution starts and where it ends. Here you can see that this instance of long function started at this time and ended at that time. Sampling doesn't tell you how many times a function was called. For example, on the sampling trace on top, you see that quick function and long function both get a lot of samples, but we don't know if it is because they were called in a loop a zillion times, or because they ran only once for a very long time, or something in between. Instrumentation will tell you information about every execution of a function. Instrumentation also gives you information about what runs concurrently to what and what happens before what. This can help in certain types of problems, like identifying missed opportunities for concurrency. For example, on the top, you have a sampling trace, this time done with call grind, and the visualization you see here is from Q-cache grind. If we look at these trays, we can see that most of the time is spent on a function conveniently called very long call. If we only looked at these trays, we would be very tempted to just optimize very long call and expect better performance. However, in the instrumentation trace in the bottom, we'll see that reducing the duration of very long call would not change the duration of the service request at all. Why? Because the service request doesn't finish until short call 3 finishes. Instrumentation shows us that in this case, the problem is that even though some functions are running concurrently, maybe some of them are not starting immediately after all the dependencies are met. For example, assuming the short calls have no dependencies on the results of other functions, they can be hoisted up and executed right when the service request starts. And then the trace will look like this. See that all the functions are nicely packed to the left. Now it would make sense to optimize very long call if it is still needed. With sampling alone, we wouldn't have figured this out, and this is something that happens in practice often. Specifically, for the case we're solving, since it gives information about individual executions of functions, it will allow us to locate outlier instances, which is exactly what we need. At the time I was looking into this, I was also working on a different tool that would allow me to instrument the given list of functions in a running task and emit their start and end times. So it came very handy. I fired up the instrumentation tool, taking the list of suspicious functions that I had identified with the sampler on the previous step. This is how our unicorn program looks using code instrumentation. You can see the same functions we saw when we did sampling, but now we see every call instance. We see the order in which they were called and concurrently to what. Note that instrumentation traces don't have thread ID information. At this level, concurrency is independent of OS threads. A call function could be a coroutine, for example, or it could be running on a Fiverr. If we zoom out and start scrolling to the right, we see a few outliers in some functions that took unusually large amounts of time, as expected. But they were not the same functions every time like I had expected. For example, you can see here how function color main takes a much larger amount of time in the instance highlighted with red than in the ones highlighted with green. You see the same thing for function pick treasure. See how much more it takes on the instance highlighted with red. The same thing happened for all other functions that were instrumented. If we kept scrolling, we would see outliers for all of them. This is not what I expected, because my assumption was that the problem I was trying to solve would happen in a specific part of the code. It didn't make sense to me that every single instrumented function seemed to have this extreme outlier problem. These are the duration histograms for some of the instrumented functions. As you can see, there are extreme outliers in every one of them. Even though their mean durations are different, they all resemble the histogram of the fetch call we saw earlier. So instrumentation is great, but like sampling, it also hides information. It only tells you when a function starts executing and when it ends. It doesn't tell you what happened in between. Maybe the executing thread gets preempted 1,000 times. Maybe there are a bunch of page faults, or who knows what other kernel surprises are happening. So once more, we have to change our approach. We have to backtrack. We're going back to sampling, but we will process the information in a granular way. We will look at every sample taken individually, and we will not aggregate them. Why do we want to do this? Because we want to be able to see exactly what's happening on every thread at the times these outlier executions happen. So I wrote a patch for my sampler tool to emit granular information and to display it sample by sample at the time each sample happened. This is what the granular trace of unicorn task looks like. And yes, I'm also using trace event format for this. And also, yes, the information displayed is different from the other trace types. Every sample is shown with its call stack with a constant width at the exact time it was taken. And every sample is in its own thread lane. In this region, the samples are distributed in a very uniform way, like we would expect, because the frequency of the sampling should be stable. But if we scroll to a time when one of the outliers execution happened, we see a gap in the samples. That is, between two consecutive samples, there's an unusual amount of time in all threads. I didn't want to believe that the sampler had a bias, so my first assumption was that whatever is causing these outliers was preventing my sampler from stopping the threads. Maybe the threads were getting stuck for a while in uninterruptible sleeps, or maybe they were hitting spin locks in kernel mode. Oh boy. Sorry. Maybe the query was causing major page faults. Maybe something was causing lots of context switches. I thought one of these was delaying the processing of the signal from my sampler to the observed task. I wrote a script to count context switches and nothing out of the ordinary came out. I looked at the reported page faults in our system monitoring and there were no peaks, at least not matching the gaps. As I seemed to have hit an impasse, I took a step back and decided to commit the granular mode patch I had made to the sampler so that I could use it in similar problems in the future. I was doing a smoke test to make sure I hadn't broken anything, and I attached the sampler to plain old cat, the task cat. As you can see, this trace of cat, the samples are evenly distributed, but if you scroll to the right, guess what? The same gaps we saw on unicorn task show up. I was heartbroken. It seemed that the sampler had a bias. It was irregularly sampling every task I ever tried it on all this time, and I had no idea. Now I had two problems to fix instead of just one. I looked at the sampler source code, looking for some obvious cause for this bias. Nothing popped up. Eventually, by looking at the traces over and over again from this angle and that angle, I finally noticed something weird. If we zoom out on the granular sample trace for cat, we can see how these gaps are spaced exactly by 5 seconds each. This gave me some joy. It was very unlikely that whatever bias the sampler could have would happen every 5 seconds. So at least I was back to having only one problem. After cat, I tested multiple tasks and saw the gaps on every one of them. So I assumed something was interrupting every single task every 5 seconds. To prove this, I wrote a small and simple Python script. All it does is this. Inside a loop, it takes a timestamp and subtracts it from the one in the previous iteration. It prints a line if the difference is higher than a millisecond, which I think is reasonable. You wouldn't expect consecutive operations to be spaced by more than a millisecond, even in an interpreted language. So basically, it constantly tests for long execution interruptions or lags. I ran it, and this is what I saw. Each one of these lines is a lag. And if you look at the seconds in the timestamps, you'll notice that they are all multiples of 5. So not only were the gaps spaced by 5 seconds, they were aligned with the system clock. This means that the problem had nothing to do with either the unicorn task all of these started with, or with the sampler. It was these lags that were inflating the latency of any task that happened to be running during a 5-second mark. The problem was in the system. My initial guess was that there was some evil task. My initial guess was that there was some evil task that every 5 seconds was spawning lots of short-lived children tasks, and that these were evicting every running task. But I didn't know what to do next. I'm an applications developer, so I spend most of my time in the land of privileged users. But fate had me run into a powerful friend who has root permissions, and I told him everything I had discovered so far. And he said, just write an eVPF script and I'll run it for you. For anyone who's not familiar with this, eVPF allows you to run sandbox programs inside the kernel and allows you to query a lot of its internal state. Amazing. Now I have the power to ask the kernel questions. So I wrote a little eVPF script that samples every core with a frequency, sampling again. If there is something running on it, it takes the thread ID and the thread name. It also gets the process ID and the process ID of the parent task. Remember that my first guess was that some task was creating lots of children tasks. So I wanted to know the parents. Finally, it takes all of these and emits it with a timestamp. I take the output and turn it into a trace events trace, once again, displaying different information. This is the 4th time I've done this. I just love the trace events format for visualization. This is what the result of the eVPF script looks like. As you can see, every lane represents a core. And every block is a constant width sample that had a thread running on it at the time. Every thread is assigned a color to make it easier to reason about them. So far, we see what you would expect. Most threads run for short periods of time and then they go back to sleep. A minority of them spend a little bit more time in a core, but most of the cores are idle most of the time. But let's scroll right to one of these 5-second marks where the lags happen and see what's going on. If you look at this highlighted area, you'll see a multitude of threads executing on every single core. And of course, kicking out any thread that is trying to do any work on them for double-digit milliseconds. These threads are our culprits. We're close to figuring this out. So what are these naughty threads? Are they short-lived tasks created by an uncivilized application like I thought at first? No. After looking at the thread names and searching for them in source code, I saw they were created by some libraries that happen to be linked in by many running applications. So I ran the profiler with the Granular patch on one of the tasks linking this library. I figured that if I looked at the samples before the lags on these threads, I would find out what they were doing to cause them. This is a trace of one of the culprit threads. In the middle, you can see one of the lags. And if you look at the last call stack before the lag, you can see there's a call to time job scheduler dispatcher. I looked at other lags in the same trace, and then I looked at lags in other tasks linking these libraries, and they all seem to be sleeping on similar code during the lags. So why is this call causing the lags? Because it runs recurring jobs starting at align times. Before we keep going, let's quickly define what a time job scheduler is, because it can go by different names like timer, event scheduler, event manager, and maybe others, and they have different sets of features. A time job scheduler is a component or utility that allows you to schedule jobs to run in the future. The functionalities vary, but it typically allows you to schedule a job to run after a given amount of time from now, and some support starting at a specific start time. Some of them allow you to schedule recurring jobs, that is, jobs that run once every period of time with a given delay. Others will force you to reschedule jobs to the recurrence. Also, some event loops and thread pools give you a similar functionality. But why the lags? Significant number of threads that are running on most backend hosts use some form of scheduling for polling, alarms, operation timeouts, heartbeats, batching, etc. Obviously, this depends on what your systems do. If you use time job schedulers for these or other form of scheduling that run recurring jobs, which will probably have delays that are multiples of 5 because we all love numbers that are multiples of 5, and kick them off with the same time alignment at the start of the hour, for example, you have a multitude of threads that will wake up at the same points in time throughout the day. So after all this preamble, the problem is just this. Thunder and herd can be caused in unrelated applications and without having any events in common. They can synchronize to wake up simply by using recurrent jobs that are aligned and have delays with a common divisor. They're not looking at the same event. They're looking at the same clock. Now, some of you may be thinking, this doesn't affect me. I don't recall seeing recurrent jobs starting at absolute times on my system. I'm pretty sure they all start at relative times. You have a good point. If the recurrent jobs are not kicked off with aligned start times, then they don't sync, and there's no thunder and herd. It's great if you don't have any or many of those. But it can still happen. Unrelated recurrent jobs with matching delays can become synced during the day. This is less likely and less problematic, but I have both observed this in the wild, and I have been able to reproduce it as well. Let's say that you have recurrent jobs A and B, like we see here. They are not synced, but they have the same delay. After some time, they both run again, still not synced. But then a period of high activity happens, maybe with higher priority threads. Then the wake-ups in these threads will be delayed together, and they will wake up together at the end of the period of high activity. They sleep again for the same delay, and then they are synced and remain synced, possibly until their tasks are bounced. Something interesting is that this period of high activity can be an existing time thunder and herd, and this syncing just recruits even more threads into it, creating a snowball effect. All of these beg these questions. Do you really need align timers on your recurrent jobs? My guess is that the majority of jobs, which are usually polling of some sort, can use relative start timers. If you need align timers, can you use your regular start times to prevent them from aligning with other jobs and thus synchronizing? If you're polling for something, can you use some form of subscription instead? If you're acting on accumulated work, can you register a job only if there is work to do? Can you use prime numbers as job delays or add random jitter? And this is how we solve the problem, by the way. If you have a custom scheduler, can it calculate all the wake-up times based on a single start time instead of the previous wake time? How can you monitor for this problem? Well, we have the script that detects the problem that I showed you before. You can use something like that to see if you have this problem. The problem with this script is that it runs without sleep on a loop, so it will take 100% of the CPU core during the entire time it runs. You could set up to run with lowest priority, but this would still be a problem from the power efficiency point of view. So if you have this problem and want to make sure you have fixed it, I propose this approach. Launch the same script a few times a day, change the launch times every day. Run for a period of 5 minutes, obviously this can vary, report any lags. This comes with a few assumptions. If there is a time thunder and herd problem with a period greater than 5 minutes, then it's not really a problem. I mean, having a small lag every 5 minutes is not really disruptive enough, but again, the 5 minutes is adjustable. If there is a time thunder and herd that happens with a frequency lower than 5 minutes, but sporadically and not for a significant amount of the day, then it must be caused by system activity. Conditions, and it's not something that can be avoided. It is just part of normal functioning. Any time herd that has a period lower than 5 minutes and occurs a significant amount of time every day will eventually be caught. If you encounter this problem, I'm very interested to hear about your experience. Please send me an email if you can. I'll be happy to keep the report anonymous if you'd like. And that's my presentation. Thanks again for listening. I hope you enjoyed it. And now I can try to answer any questions you may have.